everyone. So we're going to be taking a look at this data provided for electrical energy output, and determine and conclude what is the better model that we'll be constructing here. So in downloading the summary of information here under raw tab, we'll have all of the summary information, all the data here. We have roughly about 10,000 observations. Amongst a series of statistics here, we'll pay close attention to this correlation value matrix, as we'll be reviewing that as part of our 1 of 2 model to predict the PE score, which is what we're modeling here. We've broken down the data into 2 different sets. So here we'll have blue as well as orange down at the bottom, and that's a legend to mean our training data versus our test data. So moving into the overall basic observations of these variables, they're continuous variables. Also, we have a positive correlation between a few of these aspects, and that helps us conclude our approach. So we're going to be taking 2 approaches. First and foremost, again, we're training with about 70% of the data, and we're going to be testing with 30%. First approach is going to be a simple multivariate regression, usually a best practice first step. And on our second approach, we're going to be dropping the least correlative to PE variable, the least correlative variable, to go ahead and find out if that's a better model or not. So what we'll do, again, just steps, will be approaching the regression. The first attempt will use all 4 variables, again training with 70%. And then we're going to be calculating based off of our RMSE, MAE, MAPE, and R-square values to determine what is the better performance between these 2 approaches. For option 2, we're going to approach the same. We're just going to be using 3 variables instead of 4, dropping the least correlative variable. As we approach run 1, here we have a summary output, and a couple key highlights here is this R-squared value. So that's a very good value. So 93% of the variance is of the outcome, meaning what we're predicting for, can be attributed with these inputs. So that's very good with this linear regression. Additionally, as well as significant F here is less than our confidence level of 0.05. So that's important for us to, which basically means that this data is significant, so we can rely on it. The results of that, so we go ahead and put the raw data here, but then we end up creating a few predicted values based off of each individual observation to come up with a few analyses. And these analyses, again, the output metrics here. For right now, key particular 1 is 0.92. These other variables we're going to be comparing on our last step to find out which of these 2 models is performing better. Moving on to our second run, we're using, again, multivariate here, but we're dropping the one variable that was the least correlative. If you see here AP, RH, and V, if we compare that to here, we dropped that T since it had the least correlation to PE. In doing that, actually, our R-square goes down to 80% performance, which is quite less. But we can rely on this data. Again, this is less than 0.05, which is our threshold to determine significance of this data. We again approach the same calculations with our RMSE, MAE, MAPE, and R-squared, and we get these values. And these values are going to make a lot more sense once we come to our conclusion tab here, where we are comparing both of these runs, run 1 and run 2. RMSE as well as MAE, the lower the number the better, as this is calculating error between predicted and observed values. And also that R-square, which is a performance prediction of how much are we able to describe in our models of the variance given the performance of the model. So here it's very clear observed winner that run 1, which includes all 4 variables, is the better performing model between these 2 approaches. Thank you very much.